class, we had a small mistake that we did this question. I remember we did this question. Actually, it was correct, but actually we didn't do what is asked in the question. Actually, we have shown that fx is continuous at 0, x equals 0. But here we are asked to show fx equals sin x is continuous on R. Means that we have to prove that this function is continuous for all x. So actually in the last class we proved, but actually we proved continuous at x equals 0. So that from that we cannot conclude that the function is continuous on R. So you have to clearly read the definition of continuity. So continuity definition says, look at here, where is that? Yeah, a function is said to be continuous at A if this condition is satisfied. Function is said to be continuous on I. That is, the function is continuous throughout the domain if the function is continuous everywhere. Okay, so you have to be careful with this definition. There are two things: showing continuous at x equal a, that is one part. Okay, so let's use this one. There are two things. One is showing fx is continuous at x equal a. Okay, x equal to. So for this is a particular value. Okay, then what you have to show is limit fx extends to a equal fx. Now, if you want to show second thing, fx is continuous on I. I is the domain. Okay, so actually then your a should be an arbitrary point. You have to choose arbitrary point and you have to show this. Okay, here a is actually a particular value. Okay, so the last class actually we proved that this sin x is continuous at x equals 0. But question here is we want to prove that the function is continuous on R. Okay, function is continuous on R. So that is the thing. Okay, so what you have done is correct. What we have done is correct. But the thing is that the question is now on R. Now we'll work out that one. Okay, and we'll move to our next handout. So now we are going to prove fx is fx equal sin x is continuous on R. We are going to use the same idea, but we have to choose a different one. Okay. Now, so answer. Okay, answer. Let x naught belongs to R. So we are picking an arbitrary point. Let x naught belongs to R. Let x naught belongs to R. Then consider. So actually, what we have to prove now? Now we want to prove that. So if it is continuous on R, then we have chosen an arbitrary point. So we want to prove that limit sin x extends to x naught equal sin x naught. So this is what we want to prove. This is what we want to prove. Okay. This is what we want to prove. Okay. So we'll see how we can prove this one. Right. Now, for this one, we are going to consider this one. Consider mod of sin x minus sin x naught. So mod of sin x minus sin x naught is what? Equal to 2 times. I'm going to use sin a minus sin b. So that is equal to 2 times cos x plus x naught by 2 into sin x naught by 2. So sin x minus x naught by, okay. So I'm using sin a minus sin b. Sin a minus sin b. Now this is equal to 2 times. So we know that a mod of a into b is equal to what? Mod of a to mod of a to mod of b. So using that idea, you can write this one cos x naught, sorry, cos x plus x naught by 2 into sin x minus. But we know that mod of cos x is always less than or equal to 1, isn't it? So always mod of cos x is always mod of cos x. Cos and sin always less than or equal to 1. So I am, because I want to eliminate this cos. So, but we know that for any value of x, for all x, for x belongs to 0, 2. Okay, for any degree, okay, mod of cos x is equal to less than or equal to 1. Therefore, this part is going to be less than or equal to 1. So you can rewrite this as, so this implies as mod of sin x minus sin x naught is less than or equal to 2 times, because this part is, because this one is less than or equal to 1. Okay. So I can write it, this is less than or equal to mod of sin x minus x naught by 2. Okay, mod of sin x minus 2. But we know that again, we know that mod of sin x, this early idea, mod of sin x is always less than or equal to mod of x. Okay, therefore, now how can I write this one is this way. It symbolizes mod of sin x minus sin x naught is less than or equal to 2 times mod of sin x minus x naught by 2 is less than or equal to, here sin x is always less than, mod of sin x is always less than or equal to mod of x, no? So this one I can write it as 2 times mod of x minus x naught, right? Using this side. So this implies sin x minus sin x naught. Okay, now you can get these two to cancel. It's less than or equal to mod of x minus x naught. Now think of the definition of continuity. Epsilon delta definition. So epsilon delta definition says what? So actually what we want is in order to write limit sin x tends to x naught equal sin x naught. Actually what we want for all epsilon greater than 0 there exists delta greater than 0 such that mod of x minus x naught less than delta should imply mod of sin x minus sin x naught less than x. So now you can, from this one, now you can understand what is the suitable value for your delta. Okay. So if the delta, this one, the delta is less than, if you choose delta as something, okay, you can directly get this one. This is less than epsilon. So what is the suitable delta value? Can anybody tell me what is the suitable delta value now? So from this one, now you can easily identify the delta value. So what is the delta value? So choose. So if we choose delta equal what? Can anybody tell me what is the suitable value for delta now? Yeah. Now you can choose not the epsilon equal delta. We want to choose the delta now. So delta equal epsilon. If we choose delta equal epsilon, then we have mod of sin x minus sin x naught. Sorry. If we choose delta equal epsilon, then we can say that for all epsilon greater than 0, okay, for all epsilon greater than 0, mod of x minus x naught less than delta, which is equal to epsilon, will imply mod of sin x minus sin x naught is less than epsilon. Okay, so you can say that limit sin x tends to x naught is equal to x. Okay, since x naught is arbitrary, since x naught belongs to R is arbitrary, you can say that we can conclude fx equal sin x is continuous. Okay, so that is the idea. Do you understand? Tell me whether you understood or not. What about others? So actually, you have to get the idea. So this is actually your don't write this part. This is not actually this is actually what we want. So for that one, we are finding or we are choosing our delta. We are trying to choose our delta. So if we choose delta equal epsilon, then for all epsilon, mod of x minus x thing will imply sin x minus delta. Okay, so then you can write this one. Okay, so that's a different. So actually here we proved that at x equals 0 last time, but the question is actually continuous on R. So if it is continuous on R, you have to choose it accordingly. Yeah, right. Okay. Now we'll move to our next handout. We stopped our last discussion. I remember we discussed this question number 1. So fx equal 1 over x 0 is differentiable at x not equal to 0 with derivative f dash x equal minus 1 over x square. Okay, so actually there are two situations. Okay, so this function is defined on R. The function is differentiable everywhere except x equals 0. Except x equals 0. Therefore, we consider two cases. One is that x is not equal to 0 and we are choosing an arbitrary point on R x naught. So we are taking x naught is not equal to 0. In fact, if you want to show the function is differentiable, we have to consider this limit. I told you in the last class, there are two ways you can consider the thing. That is, one is f dash x defined two ways. One is limit fx minus f of x naught over x minus x naught as x tends to x naught. So this is one way. Alternatively, you can write this also. Limit h tends to 0 f of x naught plus h minus f of x naught over h. Either you can consider this one or this one. Okay, so in some situations this may be easy for us to derive at some conclusion. Okay, therefore mostly people use this form of definition. Okay, both are similar. We are taking x equal x naught plus h. We are taking x equal x naught plus h. Okay, so that is why we are considering this one. We are considering this one. So if you want to show if a derivative exists, actually you are considering this limit because that is the derivative. That is the derivative of the function at x equal x naught. So we are considering limit fx naught plus h minus fx naught over h as h tends to 0. Okay, then you know the function. When x naught not equal to 0, you just write the function 1 over x naught plus h minus 1 over x naught divided by h. And you do some simplification here. And this expression now reduced to this form. Minus 1 over x naught into x naught plus h. When h tends to 0, that is equal to minus 1 over x naught square. Since x naught is not equal to 0, okay, we don't have any problem with this expression. If x naught is equal to 0 only, this value tends to infinity. But here x naught, we have considered the case where x naught is not equal to 0. Therefore, minus 1 over x squared, we don't have any problem with minus 1 over x naught squared. So we can, from this one, we can say that the function is differentiable because this is a finite value. This is a finite value because the definition of differentiability is what? If you get if this limit exists, The limit exists mean what? You get a finite value for this limit. You get a finite value for this limit, then limit exists. Therefore, minus 1 over x naught squared actually belongs to R, because R x naught is not equal to 0, no? So this belongs to R. Therefore, limit exists. Therefore, we say that this function is differentiable when x naught is not equal to 0. Now, we want to, actually this question has two parts. One is we want to show function is differentiable everywhere except x not equal to 0. So now we have shown the function is differentiable when x is not equal to 0. Now we have to show the function is not differentiable when x is not equal to 0, when x is equal to 0, sorry. So now again we are using the same definition, but here our x naught is 0, x naught is 0. So I'm in the same limit. I'm considering the same limit, but my x naught is 0. Therefore, my limit will have this form. That is limit h tends to 0. Originally, actually this one. Limit, okay, f of 0 plus h. That means my h naught. X naught is 0, no? Minus f0 over h, where h tends to 0. Since 0 plus is h, that is why we have written h. Okay, don't get confused here. Why you are writing h? Because our x naught is 0. So we simplify and write it as h only. Okay, so fh minus f0 divided by h. Then you just substitute the value and then we get this one, 1 over h squared, h tends to 0. But if you evaluate this limit, obviously this expression goes to infinity as h tends to 0. Therefore, here, since it goes to infinity, the limit does not exist. So this limit does not exist when x equals 0. Therefore, we can conclude that function is not differentiable at x equals 0. Function is not differentiable at x equals 0. Okay, so that was our first question. Second question, okay, the same way. Here also the function is defined to be from R to R and given by fx equal x to the power 1 over 3. Here we want to prove the function is again differentiable everywhere except x equals 0. And the derivative is given. Normally we know the derivative, no? So using our A-level knowledge, we can find the derivative. Okay, but here actually you have to use the definition. Okay, so here they are not asking you to find the derivative of this function, because everybody knows, okay, how to find the derivative. It is a very basic function. Anybody can find the derivative of this one. So that is not the task expected here. Here we want you are tested whether you are able to use the definition of differentiability and able to show whether the function is differentiable everywhere at x equal except x equals 0. Right? Let's work out this one. Right, so example number 2. Okay, so the function fx is defined from set of real numbers to set of real number, and defined by fx is equal to x to the power 1/3. That's cubic root of x. Okay, x to the power 1. Now we want to prove this is f is differentiable on R, okay, except x equals 0. So as I told you before, there are two things. One, you have to show this is differentiable everywhere. Second thing is you have to show not differentiable at x equals 0. So let's work out this one. So as usual, we'll consider the same way. Let x naught not equal to 0. We are going to consider the first case, that is x naught is not equal to 0. X naught is not equal to 0. Now we want to consider the limit. So sorry, consider f of limit f of x naught plus h minus f of x naught over h as h tends to h tends to 0. Okay, right, h tends to 0. Now this is equal to, if you substitute the functions here, we get x naught plus h to the power 1/3 minus x naught to the power 1/3 divided by h here, limit h tends to 0. Now we want to simplify this one, x naught plus h to the power 1/3 minus x naught to the power 1/3. So how we can do this one? How we can simplify this? Because we have a kind of fractional indices. Therefore, it is very difficult to simplify. So how we can do this one? Any idea? Any idea how we can simplify this part? X naught plus h to the power 1/3 minus x naught to the power 1/3. How we can simplify? Okay, so let me give a small idea. So a plus, think of this, a plus b, a plus b minus b, a plus b minus b. I am considering this one. You can write this as a plus b to the power 1/3 to the power 3 minus b to the power 1/3 power 3. Okay, so when these two are multiplied, we will get 1 here, we will get 1 here. Okay, now we know the expansion of this one, factorization of this one. Okay, factorization of this one. Say for an example, x cube minus y cube. What is the factorization of x cube minus y cube? Can anybody tell me what is the factorization of x cube minus y? What is the factorization of x cube minus y cube? I'm waiting for your responses, please. Hello? What is the factorization of x cube minus y cube? Yes. So x cube minus y cube is x minus y into x squared plus xy plus y squared. So using the same idea, here you can write it is equal to a plus b 1/3 minus b 1 over 3, your x is this one, your y is this one, into a squared, x squared. So that is a plus b 2 by 3 plus x into y, that is a plus b 1 over 3 into b to the power 1 over 3 plus b to the power y squared, that means b to the power 2 by 3. Okay, so now look at here. Actually here what we have is this one. Now you look at the denominator, x plus x naught plus h to the power 1/3 minus x naught to the power 1/3. So similar things you have here, isn't it? Similar thing you have here. So for that one, you can put what? A plus b minus b. So let me write it this way. So from this one, you can write it a plus b to the power 1/3 minus b to the power 1/3 is equal to a plus b minus b over this part. No? So you can write it as a plus b 2 to the power 3 plus a plus b 1/3 b to the power 1/3 plus b to the power 2/3 b to the power 2. So a plus b 1/3 minus b to the power 1/3 equal to, you can write it a plus b minus b over this one. So now I'm going to replace that one. Therefore, now this is equal to this limit. This is mean this one. Huh? So this one. Now I'm going to continue this one. So that is equal to limit. I can write it x naught plus h x naught plus h minus x naught, because my a is x naught plus h minus x naught. No, so anyway, so that is a. No, so you can just put anything. Okay, don't worry about that. So this is also a. No, so b is a here. This one is b. Anyway, that is same. Okay, so it is a. So just don't worry about that. Okay. So the same thing I'm using here. Don't worry about that. Anyway, the idea is same. So idea is same. Don't worry about. So then you can write this as over x naught plus x minus. You can write it x naught plus h to the power 3 by 2 plus x naught plus h to the power 1/3 into x naught to the power 1/3 plus x naught to the power 2 over 3. And here, in addition to that, we have a h here. So that h also should be there. Then h cancels. Now, if you simplify x naught get cancelled. here there is an h, here there is an h, they are get cancelled. So this is ultimately we get limit h tends to 0 equal 1 over x naught plus h the power 2 by 3 plus x naught plus h 1 over 3 x naught 1 over 3 plus x naught. So if x naught tends to 0, we get 1 over 3 times x naught to the power 2 by 3. Okay. Since x naught is not equal to 0, this belongs to set of real. Reason is x naught not equal to 0. Okay. Therefore, fx is differentiable on r minus. Okay. fx is differentiable on r minus 0. Now, if x not equals 0, okay, so if x equals 0, if you take x equals 0, if x equals 0, if you consider the limit f of h, so f of h means you have to understand why I'm writing f of h. That is actually f of 0 plus h minus f of 0 over h tends to 0, which is equal to limit h tends to 0, h part is 0. This is h to the power 1. So which is equal to limit we have 1 over h to the power 2 by 3 h tends to 0. In fact, this limit tends to infinity as h tends to 0. Therefore, fx is not differentiable. Okay. Do you understand this? Tell me whether you understand or not. Now, the question number 3, everything is there, you can understand. Question number 3, fx is equal to x squared. Fx is equal to x squared and x belongs to it. So this is then at any x naught in R, the function fx is differentiable. And also, you want to write the difference. Here also, you look at here. Here also, they are asking the derivative. So derivative means that this is the answer, no? Therefore, you can write the derivative as fx naught. You replace by x naught. You replace x naught by x, because x naught is a arbitrary point, and now we are replacing it by x, and therefore you can write it as f dash x is equal to 1 over 3x to the power 2 by 3. The same thing, but you are writing in x instead of x naught. Okay. In earlier question also the same. Here fx is here also we want to show f dash x is equal to minus 1 over x square. and that is the expression we are getting. But here we have x naught since we choose our point as x naught. Okay, so then finally you have to give it in terms of x. Now the question number 3, fx. So that is very simple. I think you can do it, but let me show something here. Fx is equal to x squared. Okay, so function is defined from R to R. So as usual, let x naught belongs to R. Okay, here we don't need to consider x naught not equal to 0 because we want to show this function is a continuous function. Therefore, everywhere it is differentiable. Not continuity does not imply differentiability. You have to be careful. Though it's a polynomial function, therefore this function we know that this is differentiable everywhere. Therefore, we don't need to consider x not equal 0 case. Okay, so let x not equal to 0. Then consider as usual the same limit we are going to consider. Consider limit f of x naught plus h minus f of x naught over h as h tends to. So that is equal to limit x naught plus h mean we have x naught plus h all in squared minus x naught squared over h tends to. So then using a squared minus b squared form, this becomes limit x naught 2x naught plus h. Just do a small simplification here. You just factorize the numerator, then you can get this one. Cancel h up and down, and you can get this one. As h tends to 0, this becomes 2x naught. Therefore, this belongs to set of real number. Therefore, limit exists. See, so this exists. Okay, this 2x naught. Okay. So look at here how it is written. So in this case, f dash is defined. So it is defined, no? Because this is actually our f dash. So f dash x naught actually. So since it is defined for all, okay? So defined for all means because we don't have any pole. That means that we don't have any critical point here, okay? Because 2x naught is a straight line. There's no any critical point. Therefore, we can say that fx naught is defined everywhere. Therefore, you can say that fx is equal to. So you can say since f dash x is defined for all x belongs to R, you can say that f dash x is equal to. So that is very simple. And the last question here, e to the power x. E to the power x. So our function fx is our function fx is equal to e to the power x, where it is defined from R to R. How we want to show that e to the power x dash equal to. So for all R, so therefore we don't need to worry about this one. But the thing is that if you consider the limit, okay, so if you consider the limit, okay, if you consider the limit, actually, sometime it would be, because the previous question number 2, actually we use some factorization technique to simplify our expression, and we were able to show the limit is that. But this time, what we are having is exponential function. So therefore, having exponential function in our expression, is difficult for us to simplify. Therefore, we have to use some other method. So let's consider this one. For h not equal to 0, for h not equal to 0, e to the power x plus h, e to the power x plus h minus e to the power x over h, because the same thing, but we are consider for our limit, minus e to the power x. We are considering this one. We are considering mod of this one. Yes, okay. So this is what actually. Can anybody tell me what is this? This is equal to what? So you can write this as e to the power x, e to the power h minus e to the power x minus h into e to the power x over x h. So why we are considering this, you will understand shortly. Okay. So you can write this expression e to the power x plus h minus, here you may think that why I am not considering the limit. So if you consider the limit, okay, you can consider the limit, but in the second step, you will find no way to proceed. You will find no way to proceed because we are having exponential function. Therefore, we cannot use factorization. So therefore, there may be some, problem. So that is why we are considering this one, and you can understand actually this is what we consider for our limit. You can say, no, this is actually, this part is what actually f of x plus h minus f of x over h, and here minus e to the power x, because the derivative is same as e to the power x, no? That is why we are considering this one. Okay, so this is actually our f dash x. Okay, and if we can show this is equal to 0, this tends to 0 as h tends to 0, then we can say that the derivative of dash x is equal to e to the power x. So that is the idea actually. So now what we are trying to show is, if we can show that mod fx plus h minus fx over h minus e to the power x tends to 0 as h tends to 0, then we can say that f dash x is equal to e to the power x simply. Okay, so that is why we are considering this expression. That is why we are considering this expression. Okay, right. So let me show you how we can do this one. So there is no problem with this one. So now this is e to the power x into e to the power h minus e to the power x minus. So you can take out e to the power x out. Also, sorry, e to the power x. I'm writing the h also here. Then this becomes e to the power h minus 1 minus h. Okay. Now I'm considering the modulus of this one, because I want that modulus, as I just told you. Okay, now I'm considering the modulus of this one. Now consider mod of e to the power x plus h minus e to the power x over h minus e to the power x. Now we know that this is equal to mod of this one, because this is equal to this one. No? So we have e to the power x over h into e minus 1 minus h. Sorry, e to the power h. No, I'm sorry. E to the power h. Now, okay, e to the power x is always positive. E to the power x is always positive. Okay, e to the power x is always positive. So, another thing that so I forgot to tell one more thing, that this one is equal to summation n factorial over n factorial over h to the power n, where n equal to n. Sorry, this is x. So this one e to the power h minus minus 1 minus h, you can write this way. Summation n equal to n h to the power n over infinity. Why? Can anybody tell me why is that? E to the power h minus 1 minus h equal to what? So what is the expansion of e to the power x? Maclaurin series. What is the expansion of Maclaurin series? For e to the power x, 1 plus x plus x squared over 2 factorial plus x to the power 3 over 3 factorial. So this is called the Maclaurin expansion for e to the power x. Maclaurin expansion. It's an infinite series. Therefore, I'm going to write that one here. So that is what? 1. Okay, let me consider this one first. E to the power h. So e to the power x is equal to 1 plus h plus h squared over 2 factorial plus h cube over 3 factorial. So from this one, you just take these two this side. So you can write it e to the power h minus 1 minus h is equal to, look at h squared over 2 factorial, h cube over 3 factorial. Therefore, using the summation, you can write it as h to the power n over n factorial. But where n running from 2 to infinity. So this part is equal to summation h n over n factorial n equal to 2 to infinity. That is what I have written here. Okay, so that is equal to this part. So here you can write this. Do you understand this, students? Whether you understood how this came? Tell me, we are running out of time. So today we want to finish this handout. Tell me quickly whether you understand or not. Right. So now I'm going to continue this one. Now I'm going to continue this one. So that is equal to, so now I'm writing here. We have e to the power x plus h minus e to the power x over h minus e to the power x is equal to okay, is equal to, we know that is equal to this one. But again, one more thing, h to the power n, h to the power n, if h is less than 1, if h is less than or equal to 1, if h is less than or equal to 1, then h to the power n, okay, mod of h to the power n is always less than or equal to h squared. You can test for any number. You can test for any number because n is h is less than or equal to 1. If h is less than or equal to 1, always h to the power n is less than or equal to h squared for n equal 2, 3, and so on. Okay, and so on. Therefore, now this is equal to, we know that mod of right, e to the power x over h into summation. We have h to the power n over n factorial, where n goes from 2 to infinity. Okay, now this one, e to the power x is always e to the power x is always positive. E to the power x is always positive, so you can say e to the power x always positive. So you can take it out of the this one. E to the power x is equal to, okay, so this is less than or equal to, okay, look at how I'm doing. E to the power x is equal, less than or equal to mod of, okay, 1 over h into summation. Okay, we have shown that if h is less than or equal to 1, okay, h is less than or equal to mod of h to the power n is less than or equal to h squared. Therefore, this is summation h squared over n factorial for n 2 to infinity if h is less than equal to 1. Okay, because our h tends to 0, no? Normally here we are considering our h tends to 0, very close to 0. H normally tends to 0, very close to 0. Therefore, always h will be less than or equal to 1. H will be always less than or equal to 1. That is why we are having this condition. Yeah, h is always less than or equal to 1 because h tends to 0. H is very, very, very close to 0. Therefore, this condition is true. We don't need to worry about why we are considering h less than or equal to 1. Okay, now what? This is less than or equal to h squared. Now what? This is equal to e to the power x. H squared cancel. You have one more h, so I can write it as mod of h into mod of, because you don't need to put mod because n is a positive number. You can write it as summation n equal 2 to infinity 1 over n factorial. So this is equal to 1 over n factorial. What you can put? For this one, say consider again e to the power x, that is equal to 1 plus x plus x squared over 2 factorial and so on. So if you put x equals 0, okay, or if you put x equal 1, sorry, if you put x equal 1, you get 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial and so on, isn't it? So if you take these two this side, e minus 2 equal to summation 1 over n factorial, where n equal to 2 to infinity. Therefore, for this one, you can put e minus 2. So this is equal to e to the power x into mod of h into e minus 2. So now what we have done is, so far, I just summarize it. What we have done is we have shown that e to the power x plus h minus e to the power x over h minus e to the power x is less than or equal to, okay, e to the power x into mod of h into e minus 2. This is what we have done, we have shown so far. Okay, now as h tends to 0, at h tends to 0, what happens now? Limit this one, e to the power x plus h minus e to the power x over s minus e to the power x, h tends to 0. Okay, h tends to 0. This is mod less than or equal to, okay, as h tends to 0, this becomes 0. Therefore, from this, what you can conclude? From what you can conclude? Limit e to the power x plus h minus e to the power x over h. Okay, h tends to 0 should be equal to e to the power x. Okay, so that is the idea. So that is what here it is explained. Okay, so then we are saying that since h is not equal to 1, this goes to this one. From this one, you obtain e to the power x is differentiable for every x belongs to s, and its derivative is equal to e to the power x. Because we have something like this, no? So this, if you want, you can write it. Limit mod of fx x tends to 0, okay, equal to 0, equal to 0, then you can conclude limit fx x tends to 0 is 0. If mod function tends to 0 as x tends to 0, you can say that without mod that also tends to 0. There is a theorem. Okay? There's a theorem. So if you can say this. So using that idea, if this mod goes to 0, because now this function is less than 0, no? So definitely this goes to 0 because this is a mod function. This mod function always positive, always positive. Therefore, this should goes to 0 because this is less than or equal to this one. We have studied sandwich theorem. You can remember sandwich theorem. So using the sandwich theorem, this goes to 0. Okay. Therefore, e to the power x plus h minus e to the power x over h must be equal to e to the power x. Therefore, we can say that e to the power x is differentiable because this belongs to R, no, for all x. So e to the power x is differentiable and e to the power x, no, standard form. E to the power h minus 1 over h. E to the power x naught into e to the power h minus e to the power h minus h. E to the power e to the power x naught into that is also correct. Okay, yeah, that's also correct. Now e to the power h minus how you can say e to the power h minus e to the power h minus 1 over h is equal to 1. How you can say? How you can say e to the power h over, we have you studied anything something like that? E to the power h minus 1 over you studied in A level. So that is a standard form, means that actually here that's not actually standard one. If it is this is our analysis course, no, therefore we cannot use the actually this is nothing wrong, but the thing is that how e to the power h minus 1 over h came 1 is the question now. So actually we are showing that here. Okay, so this is also partially correct, but better you follow this method. Okay, so this is equal to, so you can say that e to the power x is differentiable on R, and you can say that e to the power x dash equal to e to the power x. Okay, so, right. So that's all about those four exercises. If we have time, we can discuss some more questions when we discuss tutorial discussion. Now we are going to discuss another theorem that is called the product and quotient rules. Product and quotient rules. So we know that normally in differentiation, if you have a function fx into gx, y equal fx into gx, then we know that y dash is equal to f dash x into gx plus g dash x into fx. Similarly, we know that if y is equal to fx over gx, where gx is not equal to 0, then we know that y dash is equal to f dash x into gx minus g dash x into fx over gx. So we know these things, but now we are going to prove these two things. This is called the product rule. This is called the quotient rule. Okay, quotient. So actually we are going to use the definition and we are going to derive this. Using the definition and we are going to derive this one. Okay, right, let's work out the first one. Let's look at the theorem carefully. So sometime you may be asked to prove this theorem. The proof is important. Okay, all these proofs are important. Suppose, look at the condition. Look at how we are writing the statement. Statement is also important. Writing the statement is also important. So look at the condition. Suppose f and g are defined on I. I is the domain. Okay, I is the domain, are differentiable at x naught. Okay, x naught is the point on the domain. Then the function defined by pi x equal to fx into gx is differentiable at x naught. So what we want to prove is f is f comma g. We have two functions defined on the same interval I, and f and g. Not only that, look at this function. Yeah, f and g are differentiable at x naught. Then they are defining another function, pi function. How they are defining? Then we want to show pi dash x naught. So pi is defined. Then pi equal fx into gx. Anyway, it's correct, same, but we'll write it for order. Fx into gx also differentiable at x equal x naught. So that is what we want to prove now. Okay, so now we'll work out. So we'll have this assumption f and g are defined on I, and f and g are differentiable at x naught belong to I. X naught is a point in the domain. Okay, otherwise we can't do this one. Then we want to prove pi is given by this one is also differentiable. Okay. Proof is very simple. Now we know the so we'll consider pi x naught pi x naught over h. So we'll consider this one. So this is equal to f of pi is equal to, we know that. Remember, pi is equal to what? Fx into gx naught. So using that idea, the proof is very, very simple. Okay, don't miss these kind of things in your exam, huh? If it comes for exam. So pi is equal to fx into gx. Therefore, pi x naught plus h naught is equal to what? X naught plus h into gx naught plus, sorry, pi x naught plus h into gx naught plus h minus f of x naught into fx naught. Now, I'm going to add a term, okay, and then subtract one term, okay. So look at here, f of x naught plus h minus f of x naught, okay, minus f of x naught into g of x naught plus h. Okay, so look at now. Actually, I don't have this term. Minus f of x naught into g of x naught, I don't have. I have subtracted, therefore I'm going to add it now. So plus, I'm going to put like this. How I'm going to put? I'm going to put g of x naught plus h minus g of x naught into so look at this, minus f of x naught into g of x naught plus g of x naught into f of x naught. I have added these two. I have added and subtracted. So there is no change in the formula. Now I'm going to divide it by h. So if I divide it by h, so I have pi of, on the right hand side, pi of x naught plus h minus pi of x naught. Now if I divide it by h, then this part is going to be divided by h. And if I consider limit pi of x naught plus h minus pi of x naught over h, that is the definition for pi dash x, h tends to 0, is equal to what? Equal to, I have limit h tends to 0. I have two terms. The first one is f of x naught plus h minus f of x naught over h into g of x naught plus h plus the second term, limit minus h into f of x naught. If x tends to 0, h tends to 0. Okay, if h tends to, yeah, sorry, I think So this is what actually now. Yeah, it's correct now. So this is what actually according to the definition. This is nothing but f of x naught. No? So that is f dash x naught. Here there is no any, yeah, as h tends to 0, this becomes g of x naught plus, and this is actually what? G dash x naught. And this is into f of x naught. Okay. So therefore, phi dash x naught is equal to. Do you understand this? Very simple. Nothing, just time for the sake of showing I'm doing this. See whether you understand this or not. Tell me whether you understood or not. Right. Similarly, we are defining another function, chi. Chi is equal to fx naught over. So we have the second one. So we have the function chi. Chi x is equal to fx over fx over gx, where we have the condition that gx naught is not equal to 0. We want to prove chi x naught equal to chi x naught is equal to f dash x naught into g of x naught minus g dash x naught into f of x naught over g x naught. So this is what we want to consider. So similar way you can consider this function. Consider chi of x naught. So everything is in the naught. I just write it. I think x naught plus h minus chi of x naught. You just consider this one. Chi of x naught plus h over chi of x naught plus h minus chi of x naught over h. This is equal to, according to the function definition, we have f of x naught plus h over g of x naught x minus f of x naught over g of x naught over h. So if you simplify this, this becomes f of x naught plus h g of x naught minus g of x naught plus h into f of x naught over h into g of x naught plus h into g of x naught. So whatever the terms you want, you can edit, and whatever the terms you don't want. So this is equal to, so I can write this as f of x naught plus h minus f of x naught, okay, minus f of x naught into g of x naught. So I have added this term, f of x naught into g of x naught minus, again I am writing g of x naught plus h g of x naught into f of x naught. So look at here, minus minus into minus is minus, so minus there is a plus. So I am just adding f of x naught g of x naught and subtracting f of x naught g of x naught. Okay, over I have h into g of x naught plus h. So this is actually x naught. Okay, just try to okay. So g of x naught h into g of x naught. So now if you take the limit, so here actually we have is psi dash x naught equal to, now you are taking limit. Taking limit as h tends to 0. You can write it as limit f of x naught plus h into minus f of x naught over h into g of x naught h tends to 0 minus limit g of x naught plus h minus g of x naught over h into f of x naught h tends to 0. On top of that, you have a limit g of x naught into h into g of x naught h tends to. So you have to know this one. Huh? Say for an example, if you have function like this, limit fx plus or minus gx over hx, then you can distribute the limit fx plus limit gx plus or minus over limit hx. So you can write this one. So you can give the limit to each function. If subtraction, division, multiplication, anything, you can do this one. So using that idea, if you look at this one, this is nothing f dash x. So if you simplify, you will get pi chi dash x naught is equal to, we have f dash x naught into g of x naught minus, here we have g dash x naught into f of x naught. The denominator, you look at here, denominator as h tends to 0, g of x naught into g of x naught, which is equal to g of x naught. Okay, so that is the quotient rule. Do you understand this? Hello, do you understand this? Right. So we are moving to the last. This is called the quotient rule and things. That is very simple. You can understand the theory proof is given here, and we are coming to the last rule for today. And with the next class, I will finish this real analysis. Okay. We have two more theorems. That is called the Rolle's theorem, mean value theorem, and one more, some other things also there. I will discuss that and finish it. We'll find some time for tutorial class also, because we want to do some more questions on this real analysis. In the next class, I will complete the theory. Okay. Maybe if time permits, tomorrow also we can have it. I will let you know. Okay. Now this is called the composition rule. This is very important. Definitely, you will get a question from this one. A composition rule. Suppose f is defined on open interval I and x naught belong to I, and g is defined on open interval containing y naught. Let pi is equal to g circle f. So you have studied composition function. Say we have two functions. Okay, so from here to here we have the function f. From here to here we have the function g. Now we are going to define a function from here to here. this function, we write it as G circle F. G circle F means actually G of Fx. Okay, so now we are taking this function as phi. This composition function we are taking as pi. We are denoting it by pi. Now we have two functions f and g. We have two functions f and g, and the corresponding point here x naught. Here this is y naught. Okay. Now look at this carefully. We have two functions f and g. Yeah, x naught. Yeah. Suppose f is defined on open interval I and x naught belongs to I. G is defined on open interval containing y naught equal x naught. So this is actually y naught is actually equal to what? I'm writing it. So y naught is actually equal to f of x naught. That means that the image of x naught is equal to y naught. The image of x naught is equal to y. The image of x naught is equal to y. Okay. Now, images, then we have the following. Suppose f is differentiable at x naught and g is differentiable at y naught. Then chi is differentiable at x naught. Now look at here. What is the domain? Say for an example, this is the domain. We have A, B, C. We have A, B, C. So what is the domain of function f? But domain of function f is A. Domain of function g, you know that is equal to b. Now what is the domain of function phi? What is the domain of function phi? Can anybody tell me what is the domain of function phi? So if phi is equal to G circle F, what is that? Yeah, that is the domain of function G is A. Right? So now look at this carefully. X naught is a point in A. Okay. The corresponding image of x naught is y naught. That is f of x naught equal to y. Now we have the following. It says that f is differentiable at x naught. G is differentiable at y naught, because you must know the relation between x naught and y naught. Okay, f is differentiable at x naught, function g is differentiable at y naught, then phi is differentiable at x naught, and phi dash x naught is equal to, okay, f dash x naught into g dash y naught. This is the first one. Look at the things carefully. F is differentiable at x naught, g is differentiable at y naught, then phi is differentiable at x naught, because again domain of phi is A. Therefore, the element should be here. Then phi is differentiable at x naught, and differentiation is defined by phi dash x naught is equal to f dash x naught into g dash y naught. Okay, actually, this is actually sometimes we call it as the chain rule. We call it as the chain rule actually. This composition rule is actually nothing but chain rule, but we study as chain rule. Okay, so f is differentiable at x naught, g is differentiable at y naught, then phi is differentiable at x naught, and this one. The second thing, look at the second one here. F is differentiable at x naught, g is differentiable at y naught, then phi is differentiable at x naught, and phi dash x naught is equal to g dash y naught into f dash x naught. Okay, g dash y naught into f dash. Second thing, now phi is differentiable at x naught, g is differentiable at y naught, and g dash y naught is not equal to 0. Then f is differentiable at x naught. So we are dealing with three functions. We are dealing with three functions. One is f function, g function, phi function. Actually, pi is equal to what? G circle f. Now we are going to take two things. First one, this is differentiable at x naught. G is differentiable at y naught. Then we are talking about this one. Then we are talking about this one. Then we say that this is differentiable at x naught. This is our first one. The second one is this one. This is differentiable at x naught. This is differentiable at y naught. Meantime, g dash y naught not equal to 0. That condition is important. Then we are talking about the function f. This is now differentiable at x naught. Look at, we have three functions. We are taking two functions and talking the differentiability of the third function. The first one, we assume f and g are differentiable. F is differentiable at x naught. G is differentiable at y naught. Then this function phi will be differentiable at x naught. The second situation we are taking, phi is differentiable at x naught. The composition function is differentiable at x naught. G is also differentiable at y naught. Also, g dash y naught is not equal to 0. Then fx is differentiable at x naught. Third situation we are going to talk is, we are going to consider first two functions. F is differentiable at x naught. And what is the differentiability of this one? Okay, I forgot to write this one. So this is equal to phi dash x naught will be equal to g dash y naught into f dash x naught. Here, these two are differentiable. Therefore, f dash x naught will be equal to phi dash x naught over g dash y naught. Third situation we are going to talk is this one is differentiable at x naught. Okay. This one is different. This one is also differentiable at x naught. Now we are going to talk about the third function. This will be differentiable at y naught. This will be differentiable at y naught. This will be differentiable at y naught. And g dash y naught will be equal to g dash y naught will be equal to what? Also look at this condition, because we are dividing, no? So we have one condition. Like here. Here, fx naught is differentiable and f dash x naught not equal to 0. Then y naught is equal to, okay, phi dash x naught over. Okay, so that is the big picture of this one, what we are talking now. Look at here. We have three functions. Okay, we have three functions. X naught and y naught are differentiable. X naught and f is differentiable at x naught. G is differentiable at y naught. Then pi will be differentiable and at x naught, and differentiation of pi at x naught will be g dash y naught into f dash x naught. Second situation, g is differentiable at y naught and g dash y naught is not equal to 0. Pi dash, the composition function, is also differentiable at x naught. Then we can talk about f dash x naught. And the formula will be like this: f dash x naught is equal to phi dash x naught over g dash x. Now we are talking this one, this and this one. We are taking f is differentiable at x naught, but f dash x naught is not equal to 0. Phi is differentiable at x naught. Then you can say that g is differentiable at y naught, and g dash y naught will be equal to this one. Do you understand, guys? Do you understand this? Hello, do you understand? So we have one example. With that, we will complete today's class. Okay. Show that the function ln x. Show that the function ln x is differentiable for every x greater than 0, and ln x dash is equal to 1 over x. We know this one. If you if you differentiate logarithmic function, that will be 1 over x. Now we are going to use this composition rule. We are going to use the composition rule to prove this one this time. Okay, there are different methods. Sometimes you can use the limit definition. Sometimes you can use the sandwich theorem, and sometimes you can use the composition theorem. Whatever the things, you can use it. Okay, so depends on the question, depends on the thing they are asking. We can do it in whatever the need. Now, to show this one ln x is differentiable, we are going to use the composition rule. For that one, we are taking fx is equal to ln x and gx is equal to e to the power x. So you have to choose this one. So how to choose is actually through experience, through practice. Okay, all of a sudden you can't, get the idea. Okay, now in order to use composition rule, we need two functions. Okay, one function you are taking as the given function ln x. Your fx function as this one. Gx you are taking as e to the power x. Why you are taking e to the power x? Shortly you will understand. Now I am considering G circle f. So G circle f mean what? G circle f mean G of fx. G of x. Therefore, my G of my fx is equal to ln x. So my gx is equal to what? E to the power x. Therefore, G of ln x is equal to e to the power ln x, which is equal to x. Therefore, G circle f is equal to x. You look at now, G circle f function has become a very simple polynomial function of order 1. So we know that this function is differentiable for all the value of x greater than or equal to 0. Because here we have to take we have to choose the domain such that both are defined. Okay, ln x is normally defined on positive x. We cannot define negative logarithms, isn't it? Therefore, but gx can be defined on e to the power x. Therefore, we have to take the, you know, we have to take the common domain. So what is the common domain for this one? Is actually x greater than or equal to 0. Now we are considering this one. So now you look at this one. We have chosen this function. Now we have chosen two functions. Okay, now we have chosen two functions. One is fx. Actually, we want to prove my fx is differentiable. So I want to prove fx is differentiable. So which function I want to choose? Out of these three, which is suitable? Now I want to prove my f is differentiable because I have taken my fx as the given function ln x. Okay, now I have calculated gx is equal to e to the power x, which is a well-known function, which is differentiable everywhere. Also, we have found g circle f is equal to x. These two functions are differentiable on R. We have already proved, or we have the result, or these are very, you know, popular functions, and we know these two functions are differentiable on R. Therefore, now out of these three, which we are going to use it now? Can anybody tell me? Out of these three, which we are going to use it now? Yeah, we want to use the second one because now we want to prove f is differentiable. Therefore, we know that g is differentiable, phi is differentiable, then we can use this idea. That is why here. So then this one, since g circle f is differentiable and g is differentiable, okay, g second one, for the second one we need these conditions. For the second, in order to use the second one, we need these two conditions. G circle f is differentiable. G is differentiable. And G dash x naught not be should not be equal to 0. Then you can say f dash x naught equal to G circle f dash x naught over Yes, no, sorry, this is not x naught. Why? Because the domain is different, no? So that is why we are choosing that. Look at here. So we have first condition, G circle f is differentiable. G is differentiable. Those two are there. That is phi is differentiable. G is differentiable. Also, G dash y is not equal to 0. Because we know that G dash y is equal to e to the power y. This is never equal to 0. We know that for any value of y, this is never equal to 0. For every y belongs to R. Then by the theorem, we can say that fx is differentiable for every x. Why we are saying for every x? Because you have to you have to take the common domain, because fx is defined only for positive x. No, therefore when you define G circle f, actually that is also you have to define for positive x. You can't define for negative one. So you have to understand. Okay? So we have three functions. This is actually R plus. This is actually R plus. This is your function f. This is your function g. You are taking as e to the power x. Now, this function g circle f. Therefore, since this is R plus, okay, you have to talk the domain of this one also should be R plus. Okay. Therefore, you have to talk the common domain. So one domain is this one. Okay. One domain is this one. Then you have to take the least one. Okay. This is the common domain. So in this domain only, you can talk about all three functions. One function, the domain is higher one. The other function is smaller one, means then you have to take the intersection of this domain. In that domain only, you can talk about that. That is why we are saying f is differentiable for every x greater than 0, and according to that one, f dash x is equal to g dash x over g dash x over. That is the definition, no? So we have what? What we have? We have f dash x is equal to pi dash x over g dash y. So what is the relation between x and y? That is important. What is the relation between x and y? Y is equal to what? F of x. That is the thing. Look at here. Y is equal to what? Y naught is equal to what? F of x naught. So that is why we are putting here. So pi dash x over g dash y. So y is equal to f of x. Therefore 1 over e to the power ln x. Therefore that is equal to 1 over x. Therefore we are finally concluding ln dash x is equal to 1 over x. Okay. So things are there. So this time we are using the composition rule, and we have so no proof is not necessary. Proof is not necessary, but we may ask you to state this composition rule in the examination. Okay, we may ask you to state the composition rule, and you may get a question like this. Then you have to correctly select your gx function. Okay, we may ask one of these three. This time in this question, actually we have to use the second one. Sometime you may have to use this one. Sometime you may have to use this one. So one of these three you can use it. So you have to be careful. So this is end of today, and maybe next class I will have it tomorrow if possible, and I will let you know in advance. And then with that we can finish all the theory. But we have to do some questions, more questions on real analysis, because the real analysis is not like other subject, as I always tell. Okay, so I have to do some more questions. So with tomorrow, if we have a class, we can finish the theory. We have 2 or 3 theorems: Rolle's theorem, mean value theorem, Laplace L'Hospital theorem. Those kind of things we can finish it tomorrow. So if time permits, then we have to do some questions. So I will prepare a question sheet and the worksheet and send you. You have to work first, then we can discuss. That we can plan for next week. So first you have to work, then we can discuss. Otherwise, no point. Okay. So better I have put a class tomorrow and finish it. Maybe tomorrow morning. Do you have any class tomorrow morning? Maybe from 9 to 11 or something. Then we can finish it. No, then we are leave. Do you have any class tomorrow? I also want to check my things. So anyway, I will upload this video today itself.